Hi again. The second topic that in Module 3 we spent some time on was the topic of vorticity and circulation. If you remember, the main idea there was the fact that momentum can manifest itself in two different modes. We are usually familiar with the linear momentum and use it probably more often in certain daily activities and daily calculations that we may do in our mind. And that's usually captured by velocity vector, v. Velocity vector really shows the magnitude and direction of the linear momentum that we have. We also know that we can have angular momentum, and that means that my center of mass can remain in a position fixed in a space, but I can actually rotate around that center of mass, and my rotation can have both a certain magnitude, which is the spin rate I'm rotating around my center of mass, and also can have a direction. I can rotate around my center of mass around a vertical axis or around a horizontal axis. So you have the whole angular momentum captured very similar to linear momentum by a vector called vorticity, which is the curl of the velocity vector that we have for a fluid element. Vorticity as a vector, again, has exactly similar meaning. Its magnitude gives us the spin rate of fluid elements around their axis, and its direction or its orientation gives us the axis around which the fluid elements are rotating. We saw that there is something very interesting, that for incompressible flows we can write down velocity is divergent free, or the divergence of velocity as a vector field is 0. Similarly, you can show that vorticity is also divergence free, and the divergence of vorticity is equal to 0. Then, using what probably you recall from previous courses or Module 1, Gauss theorem, or if you like, you can also call it divergence, or you can go and recall what was the name of the famous Russian mathematician who actually did this even earlier than Gauss. Using that theorem, divergence theorem in short here, we can show that since both of these vector fields are divergence free, for either of them, we can use divergence theorem and conclude that the net flux of vector field described by velocity through a closed volume should be equal to 0 in an incompressible fluid. And the same thing can be said here. The net flux of vorticity vector through a closed through the surface around the closed volume should be equal to 0. These are surface integrals, and this is vorticity vector dotted to the dA vector, which is the normal vector to the element area element that we have drawn around the closed volume. So let's think about the consequence of this. In linear momentum, we discussed the fact that if you have a velocity vector, you can always find a line that is tangent to that velocity vector. And that line is this idea of a streamline. And if you draw many different streamlines, you can actually sometimes connect them together and form what people call a stream tube. So imagine we have a stream tube that is drawn like this. And then we said, oh, okay, if this is really what we have defined for any surface area that I have, for example, the surface area around this stream tube, I can think about the flux coming in or out. Since the streamline is always tangent to velocity field by definition, the side walls will give me no flux coming in and out. But at the same time, the surfaces which are orthogonal to the velocity vector or have a different angle, the inlet and outlet, for them I can easily calculate what people call volumetric flow rate, which is the flux of velocity passing through a given area. So it's V dotted to dA integrated over the entire area. And I can calculate this volumetric flow rate getting out of my stream tube, so I call it Q out, and I can calculate this volumetric flow rate getting inside, which is Q in. And based on the conclusion that we had from Gauss theorem, which was based on the fact that velocity vector is divergence free, I can make this conclusion that volumetric flow rate getting in my stream tube is exactly the same volumetric flow rate that gets out of my stream tube. There's no way velocity can get out or in through the side walls. Whatever comes in with a certain rate should exit from the other side with an equal rate. And that's an interesting and important, is an interesting point that has an important consequence. And the consequence of it is when we see a stream tube is converging, that tells us that the cross-sectional area is decreasing. So to conserve volumetric flow rate, the speed or the velocity of fluid elements have to increase as they go through this contracting shape. And that's a physical image that we have had in our calculations and in our descriptions of fluid flow from module 1 all the way till here. But in this module 3, we saw that there is a very much parallel and equivalent statement that can be said about angular momentum. If I think about angular momentum that is captured by vorticity and the fact that it's divergence free and use the Gauss theorem on it, it tells me that the net flux of vorticity passing through a closed volume should be equal to 0. Let's see what would be the consequence of that when I consider something called vortex tube. Before constructing the vortex tube, let's think about a simple line of vorticity or omega. So if I have a vortex, I have vorticity as a vector, I can draw it here. Then I can, by definition, vortex line, very much like a streamline being parallel to velocity, vortex line is always parallel to vorticity. So I can draw the vortex line that is parallel to vorticity. And again, if I combine a bunch of these vortex lines, I can probably construct something like a vortex tube that has a shape like this. And now I can define something very much equivalent to volumetric flow rate, but I call it a different symbol, a gamma, and I call it circulation, which is the net flux of vorticity coming out of an area of interest. So it's an area integral of the flux of vorticity that is coming out of an area. And I can think about it for the side walls of this vortex tube. This integral would be 0. And the only place that is non-zero is where the vortex lines are not parallel to the surface. So that would be my inlet and outlet. And I would have a corresponding circulation coming out and a corresponding circulation coming in this vortex tube. And now that I know vorticity is divergence free, Gauss theorem tells me that the net flux of vorticity coming out of this closed volume should be 0, since the side walls give me 0 contribution to this surface integral. The inlet and outlet should be equal to each other and should balance each other. So the circulation coming in should be equal to the circulation coming out. And that's very much the exact equivalent of what we have written here for linear momentum, but now written for angular momentum. And we learned that here there is also another theorem that can help us. The fact that circulation remains constant at different points that we cut a vortex tube. You have to have a constant circulation, very much equivalent to volumetric flow rate in linear momentum. If you cut a stream tube at different positions, the volumetric flow rate at different positions should be equal to each other. This fact can also be rewritten in a different way for vorticity, because we know that by definition, circulation is defined as the curl integral of velocity dotted to ds over a closed curve C. And it is a Stokes theorem that tells us that this is equivalent. So this is a Stokes theorem that enables us to say that this is equivalent to say that it is equal to the flux of curl of the velocity field coming out of the area that is encircled by this closed curve. So a curve integral, which is a line integral over a closed curve, gets converted into an area integral of the curl of the vector field that we are interested, dotted to the element, the element of area as a vector dA. And this is very much equivalent to saying that the flux of vorticity that is coming out of area of interest. So omega as a vector dotted to dA integrated over the entire area. So in other words, whether you think of circulation as a line integral of velocity around the closed curve, or the flux of vorticity crossing enclosed area by that curve, and these two are equivalent, and the idea that directly comes from simple principles in angular momentum suggests that this circulation remains constant along the stream tube that you have drawn. This is, again, a very interesting result and will have very important consequences. If my cross-sectional area is becoming narrower and narrower, circulation remaining constant, the area is decreasing, tells me that vorticity has to increase so that the overall circulation remains constant. Very much like the equivalent we had for linear momentum. And this is very much equivalent to what we have seen in normal daily activities or in undergraduate physics or college classes. You have seen demos of it when you're, for example, a figure skater and you have you're spinning around yourself. If you want to spin faster, close your hands. You change your cross-sectional area to a smaller area, you will spin faster. If you want to slow yourself down in a spin rate, open your hands, you increase your cross-sectional area, you have to spin slower. But the idea is what is conserved is this circulation. That is the overall net flux of vorticity passing through the cross-sectional area of a vortex tube that you have drawn. We continue this review in the next video, and we will use some of these ideas of vorticity and circulation to give you guys a simple idea and simple explanation for some interesting demonstrations.